Thank you. Hi, everyone. My name is Filip Matkovic, and I'm a PhD student at the Hvar Observatory, Croatia. And my talk today will be about differences in certain physical properties of coronal breakpoints within and outside of coronal holes and their ALMA counterparts, which is part of the paper that was published a few weeks ago in the A&A. So what are coronal breakpoints, or CBPs for short? They are small-scale loops of plasma in the low solar corona that connect magnetic flux concentrations of opposite polarities in the solar photosphere. They are known to have an enhanced emission in both EUV and X-rays, but are also visible in radio emission as well. And specifically for ALMA wavelength range, what we see basically are the foot points and legs of a CBP loop structure in the solar chromosphere. And on the right here, you can see two examples of CBPs. On the left, you have the EUV emission obtained by the SDO Space Telescope. In the middle, you have the ALMA band 6 image where you see the bright CBP, which is presented here also in the SDO image. And on the very right is the magnetogram of the line of sight photospheric magnetic field, where these black and white concentrations are those flux concentrations of opposite polarities that the CBP loop connects. CBPs can be pretty much found between 5 to 60 arc seconds in diameter in the images, which is roughly between 4 to 43 megameters in size. And what's interesting about CBPs is that they are spread all over the sun, basically. You can find them in the quiet sun regions, inside coronal holes, and even near active regions. And for those of you who do not know what coronal holes are, they are regions of lower density and temperature and very high abundance of open magnetic field, which appear as dark regions in the EUV and X-ray emissions, such as this one in the background image in the first slide. So what we wanted to do here is to find if there's any kind of differences between CBPs within coronal holes and those outside in the quiet sun regions based on the observed properties, mainly here the mean intensity and projected area, which are the main topic of this lecture. And if the difference is found to be true, we wanted to investigate what could be the cause of that difference and could the properties of coronal holes might be influencing the appearance of CBPs within them. In order to do that, we have collected data from two different instruments. The first one is, of course, ALMA, where we use single dish full solar disk images in band 6 channel with a beam between 26 to 28 arc seconds. And the second instrument is the Solar Dynamics Observatory, or SDO Space Telescope, where we use the EUV filtergrams at 193 angstrom and magnetograms of the line of sight photospheric magnetic field. But before the analysis is done, the ALMA data had to be first corrected for the limb brightening effect, which is visible in the upper image on the right as an enhanced brightening towards the solar limb due to seeing higher layers of the chromosphere which have higher temperatures than those below. To eliminate this effect, we used a method by Sudar et al., which uses a center to limb brightness temperature function presented here, which is a second-order polynomial of the cosine of the angle between the low side and the normal to the solar surface. And we fit this function to the image to scale down the brightness temperature from the center towards the limb, thus producing the bottom image with no limb brightening effect present. The next step was, of course, to first extract the boundaries of coronal holes to know if CBPs lie within them or outside them. And to do so, we have used the collection of analysis tools for coronal holes, or CATCH for short, which is an intensity threshold-based software which uses EUV data to extract the boundaries of coronal holes. After that, we come to the visual detection of CBPs, or identification of CBPs, where we used Python and JHelicViewer software to look for CBPs in the available SDO and ALMA images, where we first looked for CBPs in the SDO images, because there you can more easily see the expected features of a CBP loop structure. And then we looked for those same CBPs in the ALMA band 6 image, like the one shown here below. Next, we wanted to extract CBPs from the images, and to do so, we have developed a two-step procedure method which uses edge detection procedure and background subtraction procedures, where in the first procedure, we detect the edges of a CBP in longitudinal and latitudinal directions separately to look for the pixels where the intensity gradient starts to lift off, and we take those pixels as a possible CBP edge. After that, around those lift-off pixels, we take a 3 × 3 pixel square area to calculate the mean background intensity in the corresponding pixel row or column of the image, depending on the direction of detection. And that background is then subtracted from all the pixel values in the corresponding row or column. But to the final image of a CBP, we stack the two final images, which were obtained by longitudinal edge detection and background subtraction, as well as latitudinal. We stack them together into one single image in a way that we average the values of the intensity of the common pixels, or delete them if at least one of them was below the threshold of the previous two procedures. And these final images were then taken to measure the CBP properties, here projected area and mean intensity within the outlined boundaries here shown in green. Based on the dates of the available ALMA Band 6 images and SDO images, I have selected a total of 5 different coronal holes, but for the purposes of this lecture, I will show you one of those examples, which I consider to be the best example out of the 5, denoted here as CH2, to show you the results of our analysis. So on the left, you can see the SDO EUV image and magnetogram images of the sun, and on the right, you have ALMA Band 6 image, where the region around the coronal hole CH2 is zoomed in here, where the coronal hole is outlined with either red or blue contour, and all of the CBPs that were analyzed are marked here with little circles in all of these images. In the table below, we have extracted a few general properties of each of the 5 coronal holes, like, for example, area, mean UV intensity, and unsigned mean magnetic field. And here are also present the number of detected CBPs within each coronal hole and the additional number of selected CBPs outside in the quiet sun region. Now, I will mention here that the area and unsigned mean magnetic field here will be important a little bit later in the analysis that is coming. So after the measurement of the properties is done, we use the statistical analysis to see if there is any significant difference in the observed properties between CBPs within and outside of coronal holes, where we first randomly select 2 equal-sized CBP samples, one inside and the other outside coronal hole, and then a t-test was then conducted on them. And this procedure was repeated 200 times, each time with a newly randomly selected CBP sample. And the results are shown here, specifically for the mean CBP intensity for CH2 example, where the first row shows the ALMA data results and second row SDO data. And the animation you see here shows you how the result changes depending on the size of the samples. The first figure in each row shows you the average of the mean intensity of individual samples within CH2 in red and outside in blue. And what you immediately see here, that CBPs outside, which are in blue, basically have on average higher brightness than those inside. But they also have larger dispersion around the mean value, which means that some physical conditions inside CH2 might be limiting the CBPs within it to lower temperatures than is observed outside. In the blue histogram for the t-value from the t-test, we see that this difference between 2 CBP groups is somewhere around between 2 to even above 4 sigma, which is very significant difference. And in the red p-value histogram, we see that basically all the samples lie below 0.05, which is a usual threshold used to see if 2 samples differ significantly or not. And this difference is, of course, found not only for SDO data, but for ALMA data as well. So you see the difference not only in the coronal part of a CBP loop, but in the chromospheric parts as well. And similar results were also found for the rest of the 4 coronal holes with slightly different values, but still very significant differences. The second property that was measured is the projected CBP area. And here we have a similar situation where CBPs outside CH2 have on average larger size than those inside. But the difference here is slightly lower, between 1 to around 2.5 sigma, which is not very significant, but for the larger samples used, it's still significant enough. And also for the rest of the coronal hole, the values are similar, either slightly smaller or higher. And for one example, it was even slightly above 3 sigma difference, I think, for ALMA data. So now that we have found that there is a difference between CBPs within and outside of coronal holes, we wanted to investigate if coronal hole properties might be influencing the appearance of CBPs within them. To do so, we have calculated the Spearman's correlation coefficient between the relative ratio of the mean CBP properties within and outside of coronal holes and the coronal hole area, and later the absolute sign mean magnetic field of the coronal holes. In the table here, you see the results for the correlation coefficient, where if you take all coronal holes into consideration, the correlation between mean CBP properties and coronal hole area is slightly on the lower side, meaning that there is a correlation, but a very weak one here. However, if we exclude one specific coronal hole, which is noted here as CH3, which was the least stable of the 5, the correlation coefficient only rises up, even up to 0.5 to 0.7 in value, which is very high correlation. Thus meaning that larger coronal holes might be allowing hotter or brighter and larger CBPs to form within them.
Philip, sorry to interrupt. You have 3 minutes.
Yeah. Oh, thank you. And if you look at the correlation between mean CBP properties and the absolute sign mean magnetic field, when you take all coronal holes into consideration again, you basically have no correlation at all because the value is almost 0. However, if you exclude the same coronal hole, CH3, you get quite modest anti-correlation here. So this means that higher value of the absolute sign mean magnetic field, or in other words, high abundance of open magnetic field, is limiting the brightness of temperature and size of CBPs within coronal holes to lower values that are found outside in the quiet sun. And depending on which of these 2 coronal hole properties has the dominating effect, we'll get either very high significant differences between CBPs or not very significant at all. And I will just finish the lecture here with the future work that is coming very soon, where we intend to go even deeper into analysis of the coronal hole and CBP properties to see how they evolve through time in both ALMA and SDO images, where we intend to use the interferometric ALMA data for better spatial and temporal resolution, which will be important in the evolution analysis to see how the properties evolve from the beginning to end and how they might be affecting each other. So not just coronal hole properties affecting CBP properties, but how can CBP properties be affecting even coronal holes as well. And thank you for your attention.